again, everyone. So it has been 2 days since we launched the displacement of the citrate with the phosphine. So here is the colloidal solution containing the gold nanoparticles. And now we'll have to remove the citrate excess and the phosphine excess to resuspend the whole sample in a simpler solution containing just water and the phosphine. So I will split the sample into a series of Eppendorf tubes. I will split about 2 milliliters in each of them, and then I will centrifuge the samples to remove, after that, the supernatants. So well, now samples are ready for centrifugation. One very important thing, before using a centrifuge, make sure that you properly balanced all the samples so that there's no problem during the centrifugation process. So everything is ready. All samples are properly balanced through the sample holder into the centrifuge. I can put the lid and launch the centrifugation step. So it would last 10 minutes at 15,000 Gs. Well, after centrifugation, all the samples are gathered together into one single tube, okay, to give this very concentrated solution containing the gold nanoparticles covered with the phosphine. Then we have to record the absorbance of this solution, and more specifically, the absorbance at 520 nanometers, which is usually the maximum wavelength for the absorbance of gold nanoparticles in the range of 20-25 nanometers large. Well, so as you have seen, we used a 50 times diluted solution, and we recorded the absorbance at 520 nanometers. The absorbance is 0.85. Because we have 50 as a dilution factor, we can calculate the expected concentration in terms of optical density of the stock solution by multiplying 0.85 by 50. So it means that the expected concentration would be in the range of 42.5. Now we will do the oligonucleotide coupling on the nanoparticles, and we will use oligonucleotides that contain a thiol moiety that will react very easily with the gold layer. In a sample, in an Eppendorf tube, we will first add 50 microliters of thiolated oligonucleotide, which has been diluted to 10 micromolar. Okay, so we take 50 microliters of this solution. Then we add a small amount, meaning 50 microliters of BSPP2, which is a more concentrated solution containing the phosphine. Okay, this solution is made of 20 milligrams of BSPP diluted in 400 microliters of water. Then we'll add the solution containing the gold nanoparticles. The objective is to have a potential optical density in the range of 10 after dilution in the sample. The total volume for the reaction is 500 microliters. So if I want to calculate the initial volume of my stock solution here, I have to multiply the final concentration with the final volume, meaning 10 optical density multiplied by 500 microliters, and then divide this product here by the initial concentration, meaning 42.5 optical density. The result is 118 microliters of the stock solution of gold nanoparticles. And then, because the final volume is 500 microliters, I have to measure to calculate the amount of PBS, phosphate buffer saline solution, to add to this mixture of reagents. To do that, I have to subtract the volume of each of the components to the final volume. 500 minus 50 microliters of oligonucleotides plus 50 microliters of BSPP2 plus 118 microliters of gold nanoparticles gives 282 microliters of PBS. I will mix all these reagents and leave them to react on the bench for 1 hour 30 up to 2 hours at room temperature. And because at the end I will have several samples made of adenine 4, which is one of the oligonucleotide, mixed with cuts, which is another oligonucleotide, with another sample made of adenine 8 oligonucleotide coupled to cuts, which is the last oligonucleotide, you understand that I will have to prepare several samples here containing either the adenine 4, either the adenine 8, or either the cut oligonucleotide. And because the cut sequence appears in both reagents, I will prepare one sample of adenine 4, one sample of adenine 8, and 2 samples of oligonucleotide cuts. Well, now we'll prepare the samples. So first, I will add the oligonucleotide. So 50 microliters. I take adenine 4 sample. I put it in an empty vial. Then I will add 50 microliters of the BSPP2 solution, which is here. Then I will add 118 microliters of the stock solution of the gold nanoparticles. And then I will add the PBS, 282 microliters. Here we are. So I prepared the sample for adenine 4. Okay, so it's slightly bluish. Okay, color should change later, no worries. And then I will repeat the operation for adenine 8 and 2 samples of cut aptamer. So here are the 4 samples I prepared. Okay, I will leave them on the bench for 1 hour and 30 minutes up to 2 hours. Okay, no stirring, no heating. So the reaction is done now. The oligonucleotide have been coupled on the surface of the gold nanoparticles. And just to make sure that all the gold surface has been reacted and will not react anymore, we'll saturate this gold layer with a solution containing PEG thiol. So PEG PEG means polyethylene glycol. This is a long polymer which is highly hydrophilic and that will help in the saturation of the gold nanoparticle surface. So to do that, I prepared a solution containing the PEG solution dissolved in water at 150 micromolar, and I will take 35 microliters of this solution that I will add in each of the 4 samples I prepared earlier. "35 microliters. In each of the 4 samples. So now the 4 samples are ready. We will leave them on the bench for 1 hour up to 1 hour 30 without any stirring at room temperature. And after this incubation, we will remove the excess of thiolated oligonucleotide and thiolated PEG by centrifugation. To do that, we'll do it the same way as we did before to remove the excess of citrates by using a centrifugation step for 10 minutes at 15,000 Gs. So the reaction with the PEG thiol is done now. So each sample can be moved into the centrifuge. Don't forget to properly balance all your samples. Well, now the reaction is completed. So we centrifuged the samples, we will remove the supernatant and then resuspend the pellets in a HEPS solution. So you can see the deep purple or red pellet at the bottom. I remove the maximum volume of supernatants. And then suspend the sample in HEPS. And now I get the deep red color. Okay? You will repeat this step twice to make sure that you totally removed the excess of oligonucleotide. And then you can store the sample at 4 degrees before running the biosensing assay. So during the last step, we used the nanoparticles and we grafted 3 different oligonucleotides on them. One sample was made of the split adenine 4 aptamer. The other one was made with the split aptamer adenine 8. And the last one is complementary, and it's made with the cut aptamer strand. Okay? So these guys have been grafted on the nanoparticles. Then we added a PEG thiol entity to make sure that we fully saturated the surface of the gold nanoparticles. And then we centrifuged all samples several times to make sure that we were removing all the unreacted reagents. And now samples are ready. We can run the assay. So to do that, we'll prepare a series of samples. Some samples will contain the adenosine at different concentrations. One sample will contain the uridine. So uridine is a small molecule. It looks like adenosine, but it's not. Okay, so it has a similar molecular weight. The structure is very close, but it will not fit into the pockets that will be formed by both split aptamers. Okay, this is very important. It will ensure that we can test the selectivity of the assay. Okay, and the last control will be made with the adenine 8 aptamer, which is much longer. It's named 8 because there are 8 base pairs that can be formed between the adenine 8 aptamer and the cut aptamer. These 8 base pairs, they are forming a stem made of a double helix DNA, and it will be very stable. Okay, it will be so stable that it will hybridize even though there's no target. So it will be used as a positive control. Let's do the preparation of each sample. So here is the first sample. This one contains the adenine 4 aptamer and the cut aptamer. There's no adenosine. You can see it is pink, regular color for a colloidal suspension of gold nanoparticles. This one contains the same oligonucleotides grafted on the particles, but it also contains 0.5 millimolar of adenosine. The third one contains the same oligonucleotides with an increasing concentration of adenosine at 1 millimolar. The fourth one contains 2 millimolar of adenosine. And the fifth one contains 5 millimolar of adenosine. Okay? So this is the range of adenosine we will test. But besides this sample, we also have 2 more samples. This one is made of the same oligonucleotides, adenine 4 and the cut aptamer, okay? And it also contains the uridine, 5 millimolar of uridine. And the last one contains different aptamers. It contains the adenine 8 aptamer with the cut aptamer, okay? So all these guys will be put into the centrifuge, and we will launch the centrifugation for 10 minutes at 15,000 Gs. So the centrifugation step is done. We recover the samples. As you can see, in each of them, there is a dark pellet, which is made of the nanoparticles which have been centrifuged. For sample 1, if I shake this pellet, then I recover the pink solution corresponding to the colloidal suspension of gold nanoparticles. Okay, it makes sense because there's no adenosine, so there's no aggregation of the nanoparticles. For the second sample, it's pink as well, a bit lighter. Okay. For the third one, it's still lighter. Okay, so remain a small pellet. For the fourth one, there's no resuspension. Okay. Or almost no. For 5, there is a pellet, okay? You get a colorless solution, meaning that there is a full aggregation of the nanoparticles. Sample 6 is made with the uridine, okay, which is not recognized by the split aptamers, and that should not enable the aggregation. And indeed, we recover the pink color, which is characteristic to the full colloidal solution. For the control, it's fully hybridized, so we get the pellets, okay, and almost no color in the colloidal solution. So you can see that even though we do not use any UV visible spectrophotometer, we can have an overview of the assay and get an idea about the concentration where we got the aggregation depending on the concentration of adenosine. If I take the highest concentration of an adenosine, the one with 5 millimolar, so you can see that I have dark pellets at the bottom, okay? If I take this sample, and if I use hot tap water, I will increase the temperature of the sample, and I will destabilize and dehybridize the structure, and I should recover the pink color, which is characteristic to the colloidal solution of nanoparticles. I can do the same with the sample which contains the adenosine 8 aptamer with the cut aptamer. So a few seconds, let's say like 10 seconds, under hot water. And then you can see I can recover the red color, which is characteristic to the concentration, to the solution containing the colloidal solution of nanoparticles. So this process is reversible, okay?